Hello students. In this video lecture, we are going to look at the problem of dining philosophers as well as the solution for the problem. Dining philosophers problem is one of the classic problems of synchronization. Like we have the problem of producer-consumer, reader-writer, sleeping barber's problem, and dining philosophers is one such very interesting problem. So we will first understand the problem and then we will talk about the solution for the problem. So here the problem is such that there are five philosophers who come to a hall to attend some discussion. So they are going to be discussing on a particular topic, and during the discussion, whenever they feel hungry, they can utilize the food that is served on the plates. So each philosopher has got a plate in which some food is served. It is assumed to be some kind of spaghetti or noodles, which requires the usage of fork. So each philosopher, whenever if he feels hungry and would like to eat the food, they have to acquire two forks. So there are two forks available, in the one in the left hand side and other in the right side. So they have to, each philosopher have to take two forks and then he can enjoy the food. But the problem here is that there are only five forks served for all the philosophers. So actually there should have been 10 forks served, so that each philosopher will have his own fork to eat the food without waiting for the other person, or without getting into any conflict with the other person. But for the sake of this particular problem, it has been reduced to five forks only, which means that a philosopher has to wait for both the forks to become available and then he can have the food. But this may not always be happening properly. In some situations, one philosopher may take the left fork but may not be able to get the right fork, and meanwhile another philosopher may be able to get the right fork but he can't get the left fork. But the condition here is that only if two forks are available for a philosopher, he can have the food. So this is what the basic problem we are going to deal with, and we will be finding the solution for the problem. I hope the problem is clear to you. There are five philosophers who have got food served on their table, and but to consume the food they have to successfully acquire two forks, but there are only totally five forks available, which means that not all of them can eat simultaneously. They have to somehow make a sharing of the fork without leading to conflicts. So we are now going to discuss about the details of the problem. And so here this is the kind of problem that one problem number one. So here what happens is that uh, without realizing that the next person is also trying to acquire the fork, two philosophers may simultaneously try to access the fork. So for this philosopher it's right fork, but for the other one this is left fork. So this is problem number one. They both may try to access the resource simultaneously, which we are already familiar with, and we also know the solution for this problem. That solution is simply mutual exclusion. So we have to treat this as a resource and impose mutual exclusion through some mechanism, maybe semaphore for example, so that only one philosopher is using the fork at a time. So this problem is simpler to deal with. We have we already have the answer for this problem in the name of mutual exclusion and the semaphore. But the second major problem is that every philosopher takes one fork at a time and start to wait for the other fork to become available. Now what will happen? Nobody will get the second fork, and the food will can never be eaten by any of the philosopher. This situation is what we are referring as a deadlock situation. So a deadlock situation may happen in the dining philosopher's problem if every philosopher gets one fork but not the other one, and start to wait for the next person to give up the fork he has got, and they will be waiting forever without making use of the food available. So we have to overcome both the problems. So this is the summary of the problem. The philosophers share a circular table surrounded by 5 chairs. And in the center of the table, there is a bowl of spaghetti, and the table is laid with 5 single chopsticks or forks. And from time to time, a philosopher may get hungry and will try to pick up 2 chopsticks that are closest to her. A philosopher may pick up only one chopstick at a time, but then he will try to get the second one. Obviously, she cannot pick up a chopstick that is already in the hand of the neighbor. So, when a hungry philosopher has both chopsticks, then he or she can eat the food without any issue. After that, he has to release the fork. This is the expected procedure. When there are no conflicts, one of them or some philosopher will get 2 forks, will enjoy the food and will hand over the forks, and the next philosopher can then make use of it. But it won't actually, not always this will go smoothly. That's why we need some solution. So when she is finished eating, she puts down both the forks and starts thinking again. Now these are the potential issues. Two philosophers trying to acquire the same fork. Mutual exclusion is what required in that situation. And secondly, all the 5 philosophers pick up one fork and start to wait for the second fork. This is more serious problem which leads to the deadlock. So this, now we are going to get into the solution part. One simple solution is to represent each fork with a semaphore. So that is mutual exclusion. So we are not trying to deal with the deadlock now. We are only trying to overcome the first problem, that two philosophers should not try to acquire the same fork. So we can just implement the chopstick as a semaphore, so that the initial value will be 1. The moment one philosopher acquire it, it will be reduced to 0, and the next philosopher will see it as make it as -1, and he can access the fork. So that problem can be resolved in this way. And the first philosopher has to then signal. So through the signal, he can unblock the philosopher who got blocked, and then that philosopher can start eating the food. This is a solution that overcomes the first problem. So this is how it is implemented. So each philosopher will try to acquire 2 forks. But that limitation of this solution is that it does not avoid the deadlock. So we need some other solution for tackling the deadlock problem. So we know when deadlock could happen if all 5 philosophers become hungry at the same time and each grab her left fork without without getting the right fork. So this is the problem we are facing, and we have got a number of solutions suggested. One is allow at most 4 philosophers to be sitting simultaneously at the table. That means you don't bring 5 philosophers into the table itself. So if there are only 4 philosophers, at least one person will get 2 forks, and then he will hand over both the forks, and this will become available to the next person. So in a cyclic manner, every philosopher will be able to have the forks and eat the food. This is a very limited or inflexible solution, because it is suggesting that you have to prevent the philosopher itself from entering the hall. So we can't this is not acceptable. The next solution is allow a philosopher to pick up her chopsticks only if both are available. So the problem comes only when a philosopher takes one fork and don't find the other fork. But you can make this condition such that you look for both forks, see whether both are available. Even if one of them is available, do not pick up that fork. Only if both are available, it has to be taken by the philosopher. This will avoid the deadlock problem. And the third solution is use a asymmetric solution, that is An odd numbered philosopher pick up the first her left chopstick and then her right chopstick, whereas even numbered philosopher picks up her right and then her left. So in this way, not all of them will get the left 4 without able to get the right 4. Some will get both of them, so the problem will be eliminated. Now we are going to implement a algorithm based on the second suggestion. So that is what I am going to show now. The solution is given here. So before going into the algorithm, we have got some declarations. So define n as 5, which means the number of philosophers is declared as 5, and the calculation of the left 4 is done in this way. That is, for every ith philosopher, we should know. Now we are talking in terms of program implementation. So which means that we will be declaring an array, and in that array we have to know what is the position of the left fork and what is the position of the right fork for an ith philosopher. So this logic will calculate that I plus n minus 1 modular division by n, where n is equal to 5, will tell you the index of the left fork, and similarly I plus 1 mod n will tell you the index of the right fork. So we will know the indexes, and three values are thinking is means 0, hungry means 1, eating means 2. So these values will also be made use of. Okay, now let us go into the actual implementation. This is the function of the philosopher. In the philosopher function, step 1 is he has to think. So the purpose of the main purpose of coming here is to think for some new ideas. So that is done, and after that when he feels hungry, he has to call this function take force, and I is the index of the philosopher. Now control will transfer to the take force function. So it comes here, and so now the process of acquiring the fork will commence. So step 1 is mutual exclusion. That is because I mean, two philosophers should not try to take the same fork at a time. So he has to acquire mutual exclusion. So down is nothing but semmate. Semmate of mutex. What will happen? The value gets reduced to 0. Since it is only reduced to 0, not minus 1, this philosopher is able to proceed to the next step. So he changes the state from thinking to hungry. Now because he is about to eat, he is changing the state to hungry, and test function is actually meant for testing whether both forks are available. Remember, our solution is about either you get both forks or get none of them. So that is what is being done with the help of the test function. So now control will come to test function. It checks whether the state of ith philosopher is hungry. That means he is I mean, whether this process is supposed to be handed over the fork. So it checks whether it's hungry, number 1. And secondly, it checks whether the left philosopher of this particular philosopher is not eating, as well as the right philosopher is also not eating. That means that only if both left and right are not eating, the forks must be available. Even if one of them is already eating, definitely the fork won't be available. So in that case, this function will just return back to the main to take for function, and will first increment the mutex, so it becomes 1. After that, it reduces a variable called s. S is an index which has got 5 elements for each philosopher. So semmate of s of I is called, which means that 0 will be reduced to -1, and as a result the current process will be blocked here. That is, the current philosopher will be blocked here, and he won't be able to go to the next step, which is what meant for eating the food. We saw in the previous see, this is okay. So in case if take force does not block the philosopher, he would have reached the eating part. But now that if this philosopher has been blocked here, he won't be able to eat the food. It's because either the left is eating or the right is eating. This is one scenario. Another scenario is that when nobody is eating already, that means the left and right both are available. In that case, what would have happened? We are going to see the demo for that. Okay, now once again we are taking the same code, but now we are going to assume that left and right are not eating. So what will happen? Hungry, test is called, and here what happens is that this condition is false. This condition is false. That means both the left and right are not eating. Now what happens is the control gets into the true part. So where the state of I is changed into eating, and S of I is incremented here using same signal, and as a result this 0 will become 1. And when control returns to the function, this time the down will only decrement 1 to 0, not from 0 to minus 1. So this process or this philosopher will not be blocked now. Instead he will be able to proceed to the eating stage. This is how it differentiates whether a philosopher can take force or not. Only if both left and right are in different state, like either they are in thinking state or in hungry state, but not in eating state, only in that case it gets into this part, and the S of I is incremented, which subsequently decremented, not becoming 0 minus 1. So this is the logic here. And once the current philosopher starts eating, he will complete the eating, and then he has to execute the put forks function in order to release the forks as well as to unblock any blocked philosopher. So for that also mutual exclusion will be needed, and then he will change the state from eating to thinking, and he makes a call to the test function for on behalf of the left philosopher, because if the left philosopher may have been blocked while this philosopher was eating, so he tries to unblock the left philosopher. So a call is made to test of left. The same process will take place. So it will check whether both left and right are eating or not. If not eating, it will be unblocked. Similarly, he is also trying to rescue the right philosopher, and finally he restores the mutual exclusion. So this is the idea of Reining philosopher's problem. So the problem is 5 philosopher having only 5 forks. Somehow they have to share the forks, and we need the both solutions, mutual exclusion as well as solution for the deadlock. And we have seen one of the possible solution for the problem. Thank you.